recording right now, and I believe it is. So let me go ahead and minimize this out the way. Here's the problem. Here's a chess team's practice. Notice this graph scatter plot has the matches won as a y-axis, and the x-axis is the hours of weekly practice. What we need to do is get this into Desmos so that we can run a regression, find the best regression line, and use that to predict how many hours they would have to practice if they wanted to win 30 grains based upon this data. So just so you can see how we're going to get the data into Desmos, let's make sure we can read these data points. Like, for instance, let's look at this point right here. That point right there is the point, that is the point, if I can just get this to work right here, the point that looks like is for 1 hour. When they practice for 1 hour, they won 4 matches. Okay, that's how you read the points. And that's gonna go, let's move that actually so you can see where it at. Okay, that point is, and let's do another point. Look at this other point here. This point right here, if you look at it on the X, it is halfway between 1/2 and 1. So we're going to say that is 0.75. And that is the point. And it looks like it's on the 6 for the Y. And so that point is going to go. So this is what the data, so see how we're getting the data from the points. I have another 0.75, and this time we're at 9 on the y-axis. So you can see where the points are coming from. So I put all these points into Desmos like this. So if I go to Desmos here, let me just do a brand new Desmos screen, and right here, and we'll go to the graphing calculator. We'll use a plus. We'll add a table. And you know me, I like the big text. So let me make this larger. And we can put the data in. If we can go back to where we were. Okay, I can put the 1/4. Well, actually, I'm going to start with the lowest x first. So I'm going to start with this 0.756. It really doesn't matter, to be honest, as long as you get it in there. So 0.75, and we'll pair that with the 6. And then we also have 0.75, and we'll put that with the 9. And then we also had a 1/4. So you want to continue like this until you get all the points in Desmos. And I basically have already done that on this screen right here. So when you put all the points in, you probably have to move the window around a little bit once you get them all in. Notice that your X1 is going from 0.75 to 5. So that's basically how I made sure my x-axis is going that far. And then my games won, the lowest value is 4 and the highest value is 20. So I need to make sure that my y-axis goes all the way 20. Actually, I want to make it even taller. So I'm going to go here into my graph settings, and I'm going to take the y-axis max setting right here, and I'm going to bump this all the way up to 35. Yeah, I'm just giving myself a whole lot of room on the top there, okay? And actually, it wouldn't be a bad idea to expand the x-axis too. So I'm going to go back into my graph settings, and I'm going to take my x-axis all the way out to 10 hours. Is that hours? Yeah, that's hours. Yeah, so let's take that in. So now I got plenty of room for you to see all my data points. Okay? All right, so let's do the regression. All right, we know how to do 3 regressions. Let's do the linear regression first. Y1 tilde mx1 plus b. When we run that regression, we have an R-squared value of 83.6%, which is about as best you can do with a straight line. Okay, as you can see, there's no way to draw one that goes through all of those points. So this is the best straight line regression we can use. But let's check out the other ones and see if we can get that R-squared number closer to 1. So let's try a quadratic regression. We need a y1 tilde, and for the quadratic we need a x1 to the power of 2. You can get that with shift 6 to get your power, plus bx1 plus c. And is that a better fit? Look at the R skew, R2, R squared, sorry, and you can see that it is a slightly better fit than the linear. So right now the quadratic looks like to be the best fit. Let's check out the exponential just to make sure. Y squared tilde ab to the power of x1. And if we look at the look at that one, we'll see that its R-squared value is less than 83%. So we won't be using that one. So our best regression in terms of the data that we have right here looks to be the quadratic with an 84% fit. So so we'll go with that one and see what the answer, see what it looks like. So I'm going to write a regression equation based upon this quadratic here. So I'm actually going to take this one away. I don't need it. All right, and I'm going to keep the linear around just for comparison later. Okay, let's look at this. Let's go ahead and write a quadratic regression function now, and we'll call it f of x equals, I need a, I'm writing it based upon this regression right here. So I need a is 0.13. I'm going to round that to 414 to the nearest 100 plus, I need an x squared, right? Plus b is 2.419, which I'm around to 2.42, 2.42x, plus c is 4.16, I'm rounding it, 4.16, okay? And let's see, where there, I didn't mean to put a comma there, should be a, yeah, that's better. So here's my regression, and let me hide this right now. So I'm going to use this. I'm going to use this one to predict how many. If I use the best regression, the one that fits the data the closest, that would be the quadratic. So if I use a quadratic, I want to figure out how many hours. What does x need to be for my y value to be 30? So I could guess and check if I wanted to. I could go, let's try, if I could try 5. What if they did 5 hours? Would that give me 30 games? No, that gives me 19.6. Well, what if I did 10 games? 10 hours of practice. Oh, I would win 42 games. So let's try 7 hours. Oh, that's 28 games. This is according to the quadratic. So how about 8 hours? 8 hours will put me at 32 games. So I could guess maybe 7.5 hours. If I do 7.5 hours, I'll be just over 30 games there. So, in matter of fact, if I even want to refine it even more, F 7.25, that's 7 hours and 15 minutes. I wouldn't win 30 games if I did a 7.25 hours. So that's one way in which you can answer the question. It looks like our best answer here is 7.5. Now, another way we could have done this without doing all this guessing is we could just simply we could just actually solve the equation. So let's solve the equation. We know f of x is equal to 0.14x squared plus 2.42x plus 4, let me go and pull this out, 416. What is first say if I go right below that and I type y equals, well, let me do it like the way I taught it in class. What if I let g of x be equal to, and I want this to be 30 hours. That's the 30-hour line right there. So I want to know where does my regression line, and actually, yeah, and notice that my linear regression line is still up because I never got rid of it. Let me hide it for right now. My linear regression. If I look at my best fit line, let me get rid of this right here. If I look at my quadratic and I click on the intersection, it's that if I do 7.4.59, that's about 4.5. That's about 7.5 hours. I should win 30 games. So I do almost a whole day of practice, or the equivalent of a whole day's practice. The chess team should win 30 games. And that's our prediction using a quadratic. And just for yucks, what happens if I tried the linear? You know, I still got the linear right here. If I, let me go, the linear is actually right here. What if I cut the linear on? If I use the linear prediction, I would have to practice 8.8 hours, almost 8.5, 8.4 hours to get 30 games. I'm liking the quadratic one better, okay? But I like the quadratic anyway because it fit data. The data is flowing more quadratic than linear anyway, according to the math. And so there's a run through of how you can use regressions in order to solve problems in real life.